Guys, I'm so pumped. I'm gonna see you guys on Wednesday. So let's just get right to it. But I'm super excited. I'm probably gonna talk really fast, talking really fast, talking really fast. Okay. So check our homework. Lesson 6 and 7. Here we go. All right, so today we are going to do lessons 8 and 9. And the reason we're combining them is because 8 is just the final special case of factored form, and then 9 is getting into actually solving, which is what we've been working towards, right? Algebra 1 and Algebra 2 are all about solve, solve, solve. Here's a problem, solve it. What's X? What's this? What's that? What's the variable? Go and solve it. So we're going to do two things. We're going to try to look at some special kind of factors, like I just mentioned, and then we're going to look to solve. So let's start here with a little warm up. If you want to pause for a second, just to kind of think about these, but we don't have to spend too much time. So 9 times 11, right? That should just be something, if you know your 11s tables, you just multiply by that number and then double it. So 11, 22, 33, 44, 55. So of course it's 99. I don't even really like these other two. I mean, you can do them if you want, but we really just want to think about 19 times 21. And if there's just a way that you kind of recompose it in your brain, and I'm just going to show you how I do it, and it kind of follows along with what we're going to do today. So I kind of see this as, well, what if it were 20 times 21? Because I'm good at multiplying by 20 because I know I'm just going to times 2 and then add a 0. So 21 times 2 is 42, add a 0. But I know that this was only 19. So I know that I have one less 21 in there. So I'm going to have to take out one of those 21s. 420 minus 20 is 400 minus another 1. So I'm sure maybe there's somewhere that you guys would think of the same thing, or you might have thought of reducing this to become 20, right? Reduce this to become 20, then 20 times 19 is 380, but you have to tack on an extra, an extra 19, not an extra 21. There we go. And you'd still get 399. So whatever the case is, but we're going to build on this. So we're asking ourselves, can products be written as differences? And Claire makes this claim that 10 plus 3 times 10 minus 3 binomials is the same as 10 squared minus 3 squared. And she says the same thing about 20 plus 1 and 20 minus 1. Well, let's think about this for a sec. If we see two binomials being multiplied, we can use foiling. Foiling is just a method. There doesn't have to be x's. It's just a method for us to make sure that we are multiplying binomials properly. So let's go and do that. Let's assume that we foiled. So we'll do some foiling here. So we're going to have 10 times 10. Then we're going to have a negative 3 times 10. So or 10 times negative 3, I should say. So minus 10 times 3. Then we're going to have a plus 3 times 10. And then on the last, we're going to have a minus 3 times 3. Right? Because we're saying positive 3 times negative 3, positive times a negative is the negative, and then we got our 3 times 3. So hopefully what we see here is, look, we have a negative 10 times 3, which is negative 30. And we have a positive 10 times 3, which is positive 30. So we know that these two values are going to cancel themselves out. And then we just want to represent 10 times 10 as 10 squared and 3 times 3 as 3 squared. Okay, so it does check out. These are, in fact, equivalent. And of course, I know this is 100. 10 squared is 100 and 3 squared is 9. But we're just trying to preserve this pattern here, and you'll see why. We could do the same thing for this case, but let's just assume the pattern follows, because it does. So let's use that same method to think about, well, what would 100 plus 5 times 100 minus 5? Well, what did we say? We said we'll take the one value and square it, and we'll subtract the other value and that squared. So it should be 100 squared minus 5 squared. which 100 squared is, tack on 2 more zeros, so 10,000 minus 25. So it should be what? 9975. Based on that method or that pattern, that's what we're saying. And then, well, we know that 100 plus 5 is just 105, and 100 minus 5 is 95. So let's just check it out and make sure that works. 105 times 95, sure enough, 9,975. Okay, so we're saying that there's a pattern. Let's look a little deeper. What if we go back to where we have x values thrown in? We have x's in our binomials. Well, x times x would be x squared. 4 times x would be 4x. Negative 4 times x is negative 4x. And this would be negative 4 times 4. Which, I mean, really, let's be honest, we would just say this is negative 16. I know you guys know how to FOIL, so we don't really need to do that. But look what happens. You have a positive 4x term and a negative 4x term. So those are going to cancel. So what we're left with is x squared minus 16. And if we really wanted to think about it, well, we know 16 is just 4 squared. So absolutely the same pattern holds because we're saying this is equivalent. Now, what number 4 is saying is, oh, well, what if we just change it to a plus sign? Oh, perfect. Then it should just be this. But let's check it out because we got to make sure the pattern holds. So x plus 4, the binomial squared, means x plus 4 times itself, x plus 4. So if we were to do our FOILing, we'd get x squared plus 4x plus another 4x plus 16. And in this case, we are going to have a middle term. It's going to be 8x. So it's not enough just to say you take the first term and you square it and the second term and you square it. Because this is going to be x squared plus 8x plus 16. And there will be that b term there. So there must be something unique about having one, because look at our pattern. There's 1 plus and 1 minus, 1 plus and 1 minus, 1 plus and 1 minus, 1 plus and 1 minus. So there must be some pattern. So it must be that you have a binomial with a plus and binomial with a minus. And what we should notice, guys, is that it's always the same values. Okay, so let's take this out for a spin here. So let's look at the first one. All we're trying to do is utilize this pattern to go from factored form into standard form, but quick. Because quick, we're using the pattern. So notice that it's the same two values, x and 10, but they're opposite signs in the binomial. And that's what happened up here. 10 plus 3, 10 minus 3. 20 plus 1, 20 minus 1. 100 plus 5, 100 minus 5. X plus 4, x minus 4. Didn't work when you did x plus 4 squared. So the pattern is the same values, but the opposite sign. So we know that if you take the same values and the opposite sign, then you square the first value and you square the second value and you throw a minus in between. Okay, so let's do it. So square the first value. So x squared and then 10 squared, which is really 100, but it's 10 squared, but 100, those mean the same thing. Throw a minus in between. Okay, because that was our pattern. So let's just go with it. Same thing. So first value is 2x. So 2x squared, remember this one, 2x squaring that value means you're multiplying 2x times itself. So you're really doing 2 times 2 is 4, and x times x is x squared. So there's a little wrinkle there. So 4x squared, and then our second value is a 1. So 1 squared is 1. Throw a minus sign in between. That was our pattern. And again, if we wanted to FOIL it, let's just prove to ourselves, right? Let's just take one example, and then we can be like, okay, all right, we get it. So let's FOIL it. We would get x squared plus 10x minus 10x minus 100. What happens? Plus 10x minus 10x, they cancel. X squared minus 100. So we're like, okay, all right, fine. If we FOILed, I guess. But now we don't have to FOIL every time. Okay, same thing. First value is a 4. 4 squared is 16. Second value is an x. X squared is x squared minus in between. And I'm just keeping the same order, guys. So if the x comes first, here, keep it first. If the x comes second, keep it second. That's fine. I'm just maintaining the structure. If 4 comes in front, I'll put the 16 in front. Okay, now we need to go reverse. So now we need to say, well, if I notice a quadratic that's missing a b term, right? If I notice that it's missing a b term here, I know that I should probably go back to two binomials with the same values, opposite signs. Same values, opposite signs. So we need to go forwards and now backwards. So how do we get x squared? It's going to be x and x. What number will give us 81 when we square it? We should be, our number sense should kick in and we're like, oh, that's 9. 1 plus, 1 minus. And if we foiled it, we could just prove it, but we don't need to foil it. All right, let's keep going. Same thing, two binomials. What gets us 49? That would be a 7 and a 7. And again, I'm just keeping the structure. If 49 comes in front, I put the 7 in front. Y times y will give us y squared. 1 plus, 1 minus. Keep it going. Okay, 9z squared. So just try to think about it. We have two different pieces here. We get the 9 and we get the z squared. So 3 and 3 will give us 9. Z times z will give us z squared. And then we know 4 and 4 will give us 16. 1 plus, 1 minus. Okay. That's all right, right? Just keep it moving. Who cares? The numbers get a little crazier. So we have 5t, 9 and 9, 1 plus, 1 minus. We got fractions. So what? Who cares? It still follows. Same pattern, same values, different sign. So take c and square it. And then we multiply fractions, just multiply the tops, multiply the bottoms. 2 times 2 is 4. 5 times 5 is 25. Throw a minus in between. Leave it. Leave it as fractions. I told you guys last time, you got to be comfortable with fractions. Water break. Okay, same thing. Again, it's a fraction, so what? 7 times 7 would give you 49. 4 times 4 would give you 16. Make it a fraction. D times D would give you D squared. 1 plus, 1 minus. Now, what you notice, right? What's the difference about the next one? Is that they don't have opposite signs. They're both pluses. So the pattern will not continue. I know we could foil this. Like, I don't need us to go and foil this. The point is that the pattern will not continue. So that's all that we wanted to note, is that, nope, it's not the same values, opposite signs. They're both plus signs, so it's not going to continue. And the same thing down here. Guys, what have you noticed? Minus, 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 minus. And then all of a sudden a plus? No way. No way. Not part of the pattern. Okay, the last one, I don't want you to sweat it. If you know it, great. If you're confused by it, let it go. Again, x times x would give us x squared. We know we're going to have 1 plus and 1 minus. And the question is, what value when we square it would give us 6? Well, unfortunately, it's not going to be a whole number, right? Because if we use 2, 2 times 2 gives us 4, not enough. If we go to 3, 3 times 3 gives us 9, so it's too much. So it's somewhere in between. It's actually the square root of 6. Square root of 6. Like I said, if you're with it, cool. If you're not, don't sweat it. All right, what we should notice, guys, is all these similar numbers popping up, right? 100, 4, 16, 49, 81, 25. Okay? All of these numbers we should recognize as perfect squares. So we call them our perfect squares because they come from a whole number that is squared, right? 2 squared, 3 squared, 4 squared, 5 squared. And naturally, all of these have a minus sign, right? Minus sign, minus sign, minus sign, minus sign, minus sign. So let's keep it simple. These are what we call a difference, which means subtraction, hence the minus sign, hence the difference of squares. Things that are perfect squares, like x squared or c squared or 81, 16, 36, whatever they are. So these are called difference of squares. These are our last kind of special case that there's a pattern to them. Remember, same values in the binomials, opposite signs, leads to a missing b term in our quadratic. Okay. Let's roll. Here we go. Look, I already filled this one in. It says the expression x plus 4, x minus 4 has a sum and a difference. All they mean is that there's a plus and a minus, sum and difference. And so does the x plus 8, x minus 2, a sum and a difference. But when they expand them, one of these has a linear term. In this case, that's our b term. One of these has a b term and the other one doesn't. Well, guys, the reason that the x plus 4, x minus 4 doesn't have the middle term, right, the b term, is because it follows the pattern. They're the same values with the opposite signs. So that middle term is going to cancel. It's a difference of squares. The reason that x plus 8 and x minus 2 doesn't cancel is because 8 and 2 aren't the same value. Easy as that. Difference of squares will have the same values in your binomials, different signs. Okay. Why would you do that? I don't even like this warm-up. Slice it. Slice and dice. We're done. This is what we're building towards, guys, is solving. And you have all of the steps right there. You're so ready to do it. And I'm going to prove it to you. And you're going to be like, oh, snap. I can do this. So the whole point of what we are working towards is solving quadratics. Just like you guys got really good at solving linears and nice simple linear equations in Algebra 1, we are graduating to solving quadratics. If you have some ax squared plus bx plus c, some general quadratic, and it's equal to a number, you want to find x. You're like, what x values make this true? That's what solutions are. The missing parts that make it true. Guess what? This isn't that easy to do, but you know what is easy to do? And you know what we like is making our equation into something that's equal to 0. Because then if we graph it, we just have to look at the x-axis, right? Look for x-intercepts, or 0 is such a great number to work with. Guess what? Guess what's even easier? Is if we put this into factored form and it was equal to 0. And now we're like, oh, you know what? That would make it even simpler. Because you know why? Because we can use ZPP. Ready? Here's your original. So what? Can you guys get an equation equal to 0? You betcha. Check. Can you guys factor a quadratic and put it into your two binomial pieces instead? Yes. Can you guys use ZPP? We've been doing that. We've been doing that for weeks. Solving for x-intercepts. Cha-ching. Look at that. So we have all the steps at our disposal in our back pockets. Let's just go put it together. So sure enough, Tyler's like, well, hey, I have a quadratic and I'm trying to solve it. I have some ax squared plus bx plus c, in this case c is 0, equals 99. Okay. So what did Tyler do? He set it equal to 0 by doing some balancing, by just doing a nice balancing of minusing 99 on both sides, classic Algebra 1. Then what did he do? He put it in factored form because he said, you know what? When we get two values multiplied together to give us 0, we know what to do. We split it up and we use ZPP, and then we solve the tiniest little baby equations ever. The easiest little baby equations you've ever solved in your life. Let's go and do it. No time like the present. So here we go. We've just got to put all the pieces together. That's it. Let's do it. Okay, it's already equal to 0. Perfect. Let's put it in factored form. Remember, we have an x and an x in our binomial because that's going to give us our x squared. Now, we're thinking of numbers that multiply to 15 that add to 8. Should be a 5 and a 3. And if they multiply to positive and add to positive, they both got to be positive. So we split it up. Use ZPP. Well, x plus 3 could be the 0 value, or x plus 5 could be the 0 value. Solve the little baby equations. Boom, two solutions, -3, -5. Next, please. Not equal to 0, so what? -5, -5. Got to keep it balanced. X squared minus 8x plus 7 now is equal to 0. Okay, we kept it balanced. We minus 5 on both sides. Perfect. Factored form. X and x will give us the x squared. The only factors of 7 are 7 and 1 because it's prime. And now the question is, What are our signs? Well, if they multiply to a positive but add to a negative, we need a minus and a minus. Little ZPP shows us that x equals 7 and x equals 1. Two solutions, boom. Keep it rolling. Right? And pause me at any time. Like, pause me and you do it, and then check it out. Whatever. Like, just, you want to do this on your own? Yeah, go for it. Absolutely. X times x will give us our x squared. 11 is prime, so we know we have 1 and 11. Question is, if they multiply to negative 11, we need a plus and a minus. And then they're going to add to negative 10, so we're going to give the larger 11 the negative, so that they're going to add to negative 10. Split it up. ZPP, x is negative 1, or x is positive 11. Love it. Ooh, D, they're trying to throw a wrinkle at us. So what? Guys, this is a difference of squares. 49 jumps off the page at us. Oh yeah, x squared. That's right. So we know the pattern for difference of squares is you take what value when you square it would give you 49. What value when you square it gives you x squared? 1 plus, 1 minus. That's our pattern. When we lose the middle term, we have two binomials with the same value, opposite signs. So do a little ZPP. 7 plus what would give you 0? That's negative 7. 7 minus what would give us 0? That's 7. Boom, two solutions. Okay, E's looking a little funky. So what? Let's get it into standard form. Right? Let's get this into standard form. So let's just do a little foiling here. Okay, x times x is x squared. 5 times x is 5x. 4 times x. 4 times 5. Still got your minus 30 equals 0. Let's clean it up. This will be 9 x's, and 20 minus 30 will give us a minus 10. Okay, now it looks like something we're working with. Let's do it. Put it in factored form. We know we're going to have a plus and a minus because we need numbers that multiply to negative 10. It's probably going to be 10 and 1 because we need to get 9, and 10 gets the positive, right? Because we want plus 10x minus 1x would give us that positive 9x. ZPP, bada bing, bada boom. This is it, guys. This is legit. It's too legit to quit. Can't quit because it's legit. The other day, we saw quadratics can have 0, 1, or 2 solutions. Sketch the graphs that represent 3 quadratic functions. One that has none, one that has 0. One that has 2. Ready? Here we go. Just going to do it real quick. What would it mean if it had no solutions? Right? 0. Well, that would mean that it doesn't cross the x-axis because there are no x values that will make the equation equal to 0. So we're talking something like this or something like this. Perfect. What about one solution? Well, what that would mean is that it would sit and only hit the x-axis one time. Boom, right there. Bada bing, bada boom. And of course, two solutions, what we're most comfortable with is going to be the ones that cross 2 times. Boom, 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 boom. Okay, use graphing technology to graph this. No, I am your graphing technology. You're welcome. Okay, I'm just going to tell you this real quick. Is boom, boom. Okay, I know that the y-intercept is 1, hence I have the y-intercept at 1, and I'm telling you that if you were to graph this, you would be shown that there is one x-intercept. It sits right there at positive 1. Let's go and prove it. You don't believe me? No, I know you believe me, but let's go and prove it. So it says solved using our methods now. So x squared minus 2x plus 1 equals 0. Good, it's set to 0. X and x will give us x squared. 1 and 1 are the only two numbers that multiply to give us 1. Because it's prime. So the question is, if it needs to multiply to positive 1, but add to negative 2, they both need to take the minus. And what do we notice here? Is that it's the same binomial, which we're going to start referring to as a factor. So it's the same factor that's gotten repeated. Well, so that means when you go to use ZPP, right? You go to use ZPP over here, x is going to be 1. You go to use ZPP over here, x is going to be 1. So it just turns out that x is 1, and it's the only solution, hence why it sits only at one x-intercept. So sometimes you'll just get a repeated factor. That's kind of also a special type of case. But so what? You get the same factor, ZPP, it'll give you the same answer. So there's only one solution. Perfect. Choose an equation. Are you kidding me? Choose an equation we can solve without graphing? All. Because we rock out. Okay, 2 cool downs here. You guys should be pausing on this. We got lesson 8 and lesson 9. Got to give these a shot. Okay, hopefully you paused. Again, what do we notice? Ooh, it's missing a b term. Ooh, this is a difference of squares. Nice, because 36 jumps out to me. Ooh, I know 36 is 6 squared. So a times a will give us a squared. 6 times 6 will give us 36. 1 plus, 1 minus. That is our pattern. Because if we were to FOIL it, the middle terms would cancel. But now we don't have to FOIL it every time. We don't have to FOIL it because it's a pattern and we proved it. Same thing. This is a difference of squares. 49 should jump out. 7 and 7. We know 25 is a 5 and a 5. B times b would give us b squared. 1 plus, 1 minus. Wham bam. Thank you, ma'am. What's the difference here? Not possible. Why? Because it's not a difference of squares. Boo, boo you. Not a difference of squares. Last one, don't get scared. So what? 100, 81, 16. Those are all nice numbers that are perfect squares. 10 times 10 is 100. 9 times 9, 81. 4 and 4 will give us 16. D times D will give us D squared. A 1 a plus, a 1 a minus. Look at us go. Yeah, you want us to solve 3 equations here? Yeah, I'll do it. Here we go. Okay, 11 times 1 is 11. 11 plus 1 is 12. ZPP, negative 11, negative 1. Next. Get it equal to 0, guys. That's what got to do our first step. We like things equal to 0. Ooh, this is a difference of squares, right? We should notice x squared and 4, which means 2 binomials, x and x. 2 times 2 would give us 4. 1 plus, 1 minus, which means negative 2. Thank you. Positive 2. Thank you. Get it equal to 0. X squared minus 6x plus 9. Factored form, please. 3 times 3 will give us 9. 3 plus 3 will give us 6, except they need to be negative because we're adding to negative 6. ZPP, oop, this is a repeated factor. So what? ZPP will give us only one answer, x equals 3. Guys, we are rocking out. That's what's up. So, this. Okay. Lesson 7.8, 7.9. Once again, we kind of blended the homework. It's assigned in Teams and OneNote. You need to go back at any point. Go back and scroll through the video. Find a part where you're like, wait a minute. Wasn't really sure on that. Go scroll back through the video. This is due Wednesday. I'm super excited. Not even fingers crossed. I don't know why I wrote fingers crossed. I will see you guys on Zoom on Wednesday. I'm super pumped about it. Give this your best shot. I am so proud of everything you guys are doing. Keep up all the great work. I will see you Wednesday.